Okay, so with our last 13 minutes, I'll just glaze over the different requirements. From your mission requirements, you're probably going to define the throughput or the number of channels, the amount of information that can pass primarily between the payload and the flight computer. Your onboard computer is going to be defined by all of the different subsystems. So here you'll see that table that we briefly talked about before. But if we were to go more in depth, the payload would probably require a function of pointing, of toggling on and off as commands. Your communications subsystem is going to want to process, manage the downlink, and accept the uplink. And remember, when we were talking about the communications subsystem a couple weeks ago, one of the coding schemes was demodulating and modulating your signal. So that's some intelligence that you have to account for in the command and data handling software and processor. For ADCS, you need to process gyroscope, sun sensor, and other sensor data. Maybe you also want to write different determination algorithms that are computationally intensive, like Kalman filters, integrating the sensors into one estimate, orbit propagation. Maybe you have control policies on that are encoded in your processor as well, like how to control the thrusters and reaction wheels. There's a lot of software that's dedicated to fault detection, like monitoring, identifying, and correcting failures. There is some intelligence behind power management, like when to charge, how to point your solar arrays. For thermal management, you want to think about when do I turn on my heaters, or when do I toggle my luves? Do I cool, and do I point the spacecraft for thermal? And then for utilities, there's also intelligence that you have to do for just simple math. So there's a lot of computer performance metrics that we need to think about when doing our data budget and doing our, say, like CPU utilization. Okay, for avionics requirements, when you're picking out the hardware, you need to think about the physical connections between interfaces. And then for the hardware, it's going to come with manufacturer installed software that is in the form of firmware or drivers. So you also need to account for that for your software. You also need to think about getting electronics that are radiation hardened. There's this whole section in the textbook that talks about the different kinds of failures that you can see from radiation, whether they're from single event latch-ups or upsets, or if it comes in the form of total ionizing dose. So here we have depictions of how single events can affect your electronics. It's never good, so consider getting radiation hardened electronics. And then a subset of avionics is the flight computer itself. The flight computer, you can create requirements about the amount of CPUs that you want, the clock speed, the number of cores, the memory. There are different types of processors that I've listed here where the requirements for the different like processor specifications are slightly different. We'll review those technologies tomorrow. And then your onboard clock could also have a requirement as to the timing accuracy. Okay, some software requirements. pretty lax, not as many like explicit requirements. For software, it pretty much is to get the job done for your subsystems, like making sure that they communicate on this data bus, making sure that they communicate in a timely manner and they don't get jammed up. So that touches on these more qualitative requirements of the software has to be reliable. It not only has to conduct your mission, but it also has to do it in a reliable way. And then, as you all know, the ease of use for software tools is important. So that is a performance metric that we take into account when adopting software environments or platforms. Okay, question here. If there are any mistakes found after launch, is it just mission failed? So it depends. Some software platforms allow for you to re-upload code. So in that case, you can continue your mission and potentially have a successful mission. But if there is no way to re-upload some updated version of code, then you have to do what you can with the software that you have already on there. The software, it turns out, you can think of the spacecraft as having a personality. Because testing on ground is usually not as comprehensive as what the spacecraft would experience in space, there are little quirks to the way a spacecraft can behave once it is in space. We're noticing things like this for our Neutron 1 satellite, where it's stuck in certain modes, and because we can't test it on ground and because we only have limited communications with it, we're kind of doing guesswork as to, like, I guess the personality or the modes that it's stuck in, like what's possibly in its head, how it's progressing through the different modes. Oh, and then, yeah, as you can kind of insinuate from that little bit of information that I told you, software is proven through flight heritage. Because there's a lot of personality quirks associated with flying software, this basis of reality is really hard to know until you actually fly through and succeed in your mission. Okay, last slide, process requirements. The requirements not only have to do with the mission and the hardware and software, but also how we design spacecraft. So in the process of manufacturing and assembling the spacecraft, we want to require that the engineers handle the components as you would with electrostatic discharge sensitive components. For testing, we want to see stage testing and verification, moving from component isolated testing to more integrated subsystem, then integrated system testing. The CDH lead is going to have to write isolated compartmentalized testing scripts, but also these stage testing, so the more integrated testing scripts as well. And you need to think about space environment spoofing and emulation. For transport and handling, the requirements are for the flight computer to be off and self-contained within the satellite. So a couple of questions. There exists an immense amount of software dedicated to testing that will never be incorporated into the as-flown flight software. Is that software removed once the spacecraft is sent to space? Yes, absolutely. So as much as possible, you want to condense the amount of software that you're actually uploading to your spacecraft to the smallest space possible. Ideally, your testing scripts interact with your flight software in a way that is minimally intrusive, so that your flight software doesn't have to be modified to do the ground testing. So for that reason, you want to have test setups like this ADCS test facility that is as much like the space environment and as much like the physical components that you're actually going to use during ground testing, so that your flight software is as similar as it can be to what you've tested on ground. Is it possible to emulate the radiation in space? I think yes. You can emulate radiation in space by actually putting it in a physical test bed that shoots radiation at your electronics. Or what you could do is, if you do know the frequency of single events, like bit flips, what you can do is like write a random noise generator that flips bits within the electric signal line to put your spacecraft into, say, a failure mode and to test out how it would handle that failure. Okay, end of lecture. Answered all questions.